In this example, I'm going to show you how to write a formula for the general term or n term of the sequence. Before I'm going to start, I'm going to remind that I know that a sub n is the notation of the sequence. A sub n is called the term, and n, this n here, is mean the term number. So part A, we have 1, square root 2, square root 3, 2, comma, dot, dot, dot. That is our sequence. Solution. To do this, I found it easy to draw the table, like so. I have a term number and a term down here. For a term number, I have 1, 2, 3, 4, and dot, dot, dot to n. So, our term number 1, I have 1. And I have a square root 2, square root 3, square root, and then I have 4. Now it gives me I have 2. Then dot, dot, dot. I need to find a formula for that. This is the same thing as the square root of 1. This is something like square root of 4. Because the square root of 4 is 2. So if you rewrite like that, the square root of 1 as a square root of 1 and 2 as a square root of 4, I see that inside the radical, it is this number here and this number there is exactly the same as the term number. So this means our general form or our general term should be the square root of n. So our secant can write as, so the secant can be write as the square root of n. As the square root of n. So that is our answer. Can it be correct? Can be written the square root of n. Let's try part B. Let's see how we do. Part B, I'm doing the same thing. I draw the table. I have a term number and a term, and I have 1, 2, 3, 4, dot, dot, dot to n. So, and our term will be, the first one is 1/2, 1 over 3, 3 over 4, 4 over 5, dot, 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 dot. Now we need to find out the general term for that. Now I see that the n term in the table can be obtained by observing that for each term in the sequence here, the numerator, you see the numerator here, 1, 2, 3, 4, it's the same as the term number, 1, 2, 3, 4, and then n. So I must have n here, okay? And the denominator, I have 2, 3, 4, 5. The denominator actually is just 1 greater than the term number. See, my term number here is 1. So our denominator here is 1 plus 1, so I got 2. The term number here is 2, so therefore right here you see that 3 can rewrite as 2 plus 1. So actually, so you see all the denominator here is 1 greater than the term number. So I can rewrite that as n is the term number, 1 greater, so I plus 1. So the secant, so our answer should be the secant can be written as n like that, and set the dot here. So now when I go to this here can go on to n, can go to infinity, from 1 to infinity. Okay, let's try part C. See how we do with part C. Here I have a sequence. And do the same thing and draw a table. And I have n times 1, 2, 3, 4, and n, and then dot, dot, dot. You can go to infinity if you like, but I need stuff for n here. I'm going to write down the term 1/2, 1/4, 1/8, 1/16, dot, 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 dot. I want to find the general term for n term for the sequence. And I see that the n term in this table is obtained by rewrite the denominator here as 2, that's 2 to the first power, to the second power, to the third power, to the fourth power, and so forth. And I also observed that the exponents for each term it is same as the number, as the term number here. 1, 2, 1, 1 here, 2, 2 there, 3, 3 the same here, and 4 the same as the term number here. So therefore, my next one, the next term or n term for this sequence, I can rewrite as 1 over 2 to the n power. So therefore, I'll answer the sequence can be written as 1 over 2 to the n, where n, the sequence here can go from 1 to infinity. So you could continue if you want to go to infinity. But this is a general formula for this sequence.